Hello?
All good. Yep.
Okay. So my paper was on the 1992 collapse of the Atlantic cod industry in Newfoundland, and I was searching for an integrated approach to increase and stabilize cod populations. And my mentor was Neil Walker. So here we have an image of the Atlantic cod, or Gatus mora, which I'm sure many of you have eaten before, whether it's in a fish taco or in fish fingers or lightly buttered. Cod are an extremely popular fish for human consumption, and because of that popularity, there is a high demand for them. So just some facts about cod. They have a barbel chin, they have a barbel on their chin and a broom-shaped tail. They're 200 centimeters in length and weigh up to 30 kilograms, and they can live up to 25 years. They sexually mature between the ages of 2 and 4 and spawn on the sea floor. They have a very specific temperature they require for spawning, so in order to have babies, it must be between 0 to 12 degrees Celsius. They are omnivorous, and an estimated of 70% of cod have been fished. So now on to cod distribution. Cod live anywhere south as South Carolina to Greenland. They live in the Atlantic in the highlighted green area, as you can see. But for my paper, I focused right here on the cod population in Newfoundland, Canada. So a little bit about Newfoundland. The cod has been recorded as being fished since 1492, and their main fishery has been oriented around cod. Cod fishing first became a dilemma in the 1800s, when protests arose due to more industrialized equipment being used to fish cod, which scared a lot of fishermen, thinking that the cod population would decrease. So protests started, and they would destroy the equipment. And so long-term efforts did not prevent the collapse. The cod moratorium was declared in 1992, and that closed the cod industry permanently, resulting in the immediate loss of 30,000 jobs. And afterwards, Newfoundland still suffered 2 times the unemployment rate and a 10% loss in population. So the purpose of this paper is to analyze the many contributing factors that affect cod populations to this day, as all factors affect stock status. And I also hope to give policy suggestions and hopefully bring cod and the industry back. So now on to historical factors. As I stated before, there have been efforts for cod's conservation for almost 200 years, and the collapse is largely attributed to stock assessment errors. Stocks are typically assessed by fish abundance surveys and observed data from fish caught in the industry, and then those are used as guides for the fishing industry. So stock assessment errors are typically caused by the high price of stock assessment and a general lack of interest in stock assessment, and this can lead to optimistic fishing, in which high amounts of fish are fished optimistically, assuming that it will not have an effect on the population, which obviously was not true for cod. Cod were also subject to high amounts of recruitment fishing, in which the most fit and largest individuals are targeted, which is particularly impactful for cod as they take 2 to 4 years to sexually mature. It is crucial to understand these mistakes and learn from them. So now onto the anthropogenic factors of cod. So anthropogenic factors are defined as human-caused factors that affect the environment. So obviously the biggest human-caused factors is climate change. Cod are very sensitive to ocean temperature, and the NOAA released a climate change document in the 2020 stating that the average global temperature has increased 18 degrees Celsius since 1881. So because of this ocean temperature increase, this is particularly affected since 95% of size variability in cod is due to temperature. Sexual maturity decreases a year for every 2 degrees of increased bottom temperature, and then also they require 0 to 12 degrees Celsius to reproduce. Ocean acidification also poses a large threat to cod, as it causes tissue damage that is lethal to larval cod. Overfishing, Newfoundland has also not learned from their mistakes in the cod industry, and they are continuing to overfish, but this time of snow crab, which is actually an important prey to Atlantic cod. The increasing vulnerable state of cod calls for more precautions that need to be met when assessing stocks. So now on to environmental factors. So the collapse of cod led to the obstructed ecological role and a trophic cascade. This is also particularly impactful for cod as they have a strong effect on prey prey size distribution, resulting in large densities of preferred prey sizes for cod than in the absence of cod predation. So essentially, cod shapes their prey and their environment for their own benefit. Without that, their environment kind of collapsed, leading to a decrease in their size. So also because the cod population is a lot smaller, they're less diverse and therefore more vulnerable to disease and parasites. So now on to my suggestions. I suggest the establishment of a static no-take marine protected area in which no fishing would be allowed. This would cover the breeding and feeding grounds of cod, and I also recommend the extension of a moratorium to include recreational fishing. We know that MPAs are successful because of the Apo Island MPA, which is a great source. They were severely overfished as well, and they established an MPA which led to the spillover effect from jacks, which are fish that occupy a similar ecological role as cod. So at Apo Island, the fishery yield increased severely, and the standard of life also increased because it was community managed, so they got money from that. So I recommend that this MPA is also community managed to decrease unemployment in Newfoundland and help cod populations and their prey. So conclusions. There is a fantastic lesson of conservation and human greed in the Atlantic cod moratorium. The struggle for proper fishing management for cod has been going on for 200 years, yet nothing has been done. Cod are an extremely popular fish that have been heavily researched, yet they still not receive the proper conservation efforts. I hope that my suggestions will help benefit cod in the future, and we can learn from these errors and help future conservation efforts. Thank you.
Thank you so much, Sage. That was really informative, and I loved hearing your presentation. For our audience members, you can ask questions in the chat or the Q&A in the sessions tab towards the side. Or if you would want to come on camera to ask a question, you can also request and I'll see you pop up and I can have you share out that way. So if you have questions for Sage, now's the time that you can ask them away. So we have a question in the chat. Approximately how long would it take to replenish this population if fishing was halted?
That's a little unknown because fishing has been halted for over 20 years, and there is still not been a increase in cod population. So what I would recommend is the continuation of the moratorium and an MPA until there is a scientific increase in the population.
I'm also interested in that other example. Oh, here's another question. How do you think we can repurpose conservation efforts for other fish for cod?
Obviously in a similar way. So establishing an MPA would not only benefit cod, but all of their prey in the area and in that ecosystem. So from snow crabs to even shrimp in that area, they would all benefit. So it's pretty similar for all methods of ocean conservation, but obviously depends on like the migratory status of the species and where they live.
And were they able to see that with the establishment of the other marine protected area that you had talked about? Did it have kind of a trickle effect?
Yeah. Yeah, it helped all aspects of their ecosystem.
Cool. Another question. What's the biggest fallout if overfishing doesn't stop?
Well, if overfishing doesn't stop, we'll definitely see an increase of moratoriums that the government will declare, so that'll decrease jobs, and then also you'll see more trophic cascades and potentially extinctions. So obviously when that happens, that can affect an entire ocean ecosystem, if not the whole ocean.
Great. And I'll take this one last question, and thank you so much for your time. How do these MPAs get started? What's that process like?
It's a pretty difficult process to get an MPA started. So obviously you would have to go to government officials and request it. You have to have a lot of stakeholder work in it, and it can be a process of 10 to 20 years, especially in Newfoundland when fishing is one of the main sources of income. A lot of people will be opposed to it, but if enough science is shown and enough people are educated on the impacts, then it can hopefully speed up the process.
Awesome. Great job. Thank you so much. And you can click leave up in the top chat to stop sharing your screen. Victor, I'm about to pull up you, so make sure you have your presentation. You're getting that all set up. Thanks again so much, Sage. Hi.
Is my can you see my presentation?
Not yet. Can you try to share it now?
Oh, hold on. I might have to. Here it is. Okay. Right. So awesome. My presentation. Oh, sorry.
Nope, no worries. Go for it.
Yeah. So my presentation here is about Maxwell's equations and how they shape our everyday lives. This is a physics paper, but a little bit about me. You know, I play tennis, I play instruments, I like working out, I like reading about math and history, but physics has, you know, a special place in my heart. And I really wanted to learn about magnetism. So I decided to do this project. So basically electromagnetics is the study of how charges and magnets interact. And James Clerk Maxwell was a physicist who wanted to describe these in a really elegant way. And he did so in the form of his 4 equations in terms of vector calculus. And electromagnetics obviously powers all of our computers and stuff like that. But, you know, it plays an integral part in, you know, how life exists. Why don't we fall through our chairs when we sit in them? How do our nerves work? And really, you know, since we have such a big motivation for learning these, I feel like more people should know about it compared to how many people actually know about it. So the fundamental part of electromagnetics is charge. And it's really similar to mass. We can't really describe it, but we can understand it through human experience. So a couple things about charge is it's conserved. You can't create it or destroy it. Pretty self-explanatory. It's quantized, which is something mass doesn't do. Charge actually comes in little small packets, and the smallest of these packets are electrons. And so that's where electromagnetics really focuses, is on how electrons behave. And obviously charge is dual. You obviously have plus and minus charges. And then you have magnets, and those are really similar, except instead of plus and minus, you have north and south. And the reason why we're so interested in charges and magnets is because these things produce fields, electric and magnetic fields, and these fields have the ability to cause change or do work. And that's why we're really invested in doing these and in studying this, so we can understand how to control them and how we can improve our lives. So here we have our 4 equations: Gauss's law of magnetism, Faraday's law, and the Maxwell-Ampere law. And now really these look complicated, but I'm going to explain to you, hopefully intuitively, what they really mean. So starting off with the first law, Gauss's law, describes how, you know, static electric fields operate. And what it essentially says is if you have an electric field, you can make the electric field smaller by adding more charges. And my favorite demonstration of this is the use of something called a capacitor. And how a capacitor basically works is, say I have a bunch of minus charges on this pencil, and I have, you know, maybe some neutral charges over here on this other pen, and I bring them closer. Since opposites attract and like charges repel, all the minus charges on the pencil repel all the minus charges on the pen, making this effectively a battery. And capacitors are used in all sorts of electrical appliances, and without them, really, we wouldn't be able to use most of the stuff that we have. And, you know, this use of stuff, like, it's very similar to a battery. They're used in cars, they're used in solar power, and they're really quite effective and interesting. The next law, we have Gauss's law of magnetism, and it's essentially the magnetic version of the first law, except it seems really weird because why would the strength of a magnetic field be 0? And that's because north and south poles always come together. You can't have a north pole without a south pole. And this really brings the question, what is a magnet? Because obviously electrons represent charges, but what particle represents magnets? And that we probably think that there's no particle. And what happens is magnetic fields are formed by charges moving around. So if I have this pencil and pretend it's a wire, and I can have a current running through it, meaning that charges are moving, what happens is that a magnetic field forms around this pencil, and it's shaped sort of like a loop. And what we can do is we can manipulate wires and create coils called electromagnets that look like this. And then we can strengthen the magnetic field so it looks something like this. See how it would go in the coil. And these electromagnets are really important. They're very similar to capacitors. They can kind of store charges. You can even use them to make little guns. And they're really quite neat things. And then we have probably the most important part of electromagnetics, electromagnetic induction. And here you have the 3rd and 4th laws. And what these laws state is If I have moving charges to create a magnetic field, can I have a moving magnetic field to create moving charges? And the answer to that question is absolutely yes. And that's how electric generators work, is if you have a very strong magnet and you have a loop of wire in it, if you start moving the wire or changing the magnetic field, you start to have a current running through the wire. And this powers everything in our lives. And this current in the wire goes through transformers, goes through power lines, is in our wall sockets. And it's what really holds the whole power grid together. And then the other part about these two laws, and I think this is the coolest part of electromagnetics, is electromagnetic waves. So if I have an electric charge that I move up and down, there's going to be a magnetic field that moves left to right of it. But that magnetic field is going to create another up and down electric field. And that process continues, and this self-propagation creates an electromagnetic wave. And what Maxwell did, which was incredible, is he designed these equations that could be applied to almost every single situation that deals with electromagnetics. And he could manipulate them and figure out that there is a wave made of electric and magnetic fields that has the same speed as light. And therefore, he concluded that light was an electromagnetic wave. And these electromagnetic waves are really what kind of powers this new age of electromagnetics. And you obviously see this in light, microwaves, radio, X-rays, and it's really what kind of brings us into the modern world. So for this research project, I wrote a paper, but also I had these little projects. So in the middle, there's these two capacitors that I have, and my goal was to try to make as big of a capacitor as I could. And so I would do this by manipulating these two different plates, these two different electrically conductive plates, and manipulate how close they were together, what was between them, to try to get something that could hold a lot of charges, something that could do a lot of work. And here on the right, or on the left rather, we have a Van der Graaf generator. And how this works is, say I take a balloon and I rub it on my head, I get electric charges. Say if I had a motor running a belt on a piece of plastic, I could do this a lot faster and a lot more and get a lot more charges. And this Van der Graaf generator can generate thousands and thousands of volts and can generate lots of charges and do lots of work. So much that these Van der Graaf generators were used as early particle accelerators, which make them really interesting to me. And then on the right, we have my final project, which doesn't look like much. It looks like scrap, but it's really a homemade radio. And how it works is the radio waves that we constantly swim in are absorbed by an antenna. And through electromagnetic induction, I can take these radio waves, amplify them, and then kind of tune this electromagnet and this capacitor that I have, and I can plug it into a speaker, or I've replaced it recently with an earpiece, and actually listen to radio from my own home out of things that I could just buy from Home Depot. And so really the point of all this is I wanted to bring the idea of electromagnets to the people, because I think this is such an important topic that almost nobody knows about, but it's so important to us. And I think like these little things like charges that we don't even see in our everyday lives, more people should know about, more people should understand. And by doing so, we can further, the human condition and make our lives better for everybody. Thank you.
Awesome. Thank you so much, Victor. I love the demonstrations that you were able to have those materials with you too. That's awesome. Yeah. So likewise, if you have any questions, feel free to put them in the chat or in the Q&A section. If you want to ask a question face-to-face, you can also request to share your screen. I'd love to hear a little bit more about what you think like the future direction of this kind of work in electromagnetism is like, right? Like on the horizon of emerging technologies, what's kind of a really exciting application of this?
Yeah, so with capacitors, they're actually making stuff called supercapacitors. What capacitors store, they store energy through electric fields. They store these electrons, but batteries store them chemically. And what supercapacitors do is they kind of get the best of both worlds. And they're trying to use this technology and things like electric cars and things like solar power. The big issue with solar power is it's really hard to store this energy. The problem with capacitors is they charge relatively quickly, but they also discharge quickly. So you need huge capacitors. But these supercapacitors, using this chemistry, you can reduce the size, and hopefully this can be a solution to the solar panel problem, or the solar power problem, rather.
That's really exciting. Awesome. How difficult was it to make the radio? And would you be able to put together a guide for someone else to do it and learn about the relevant equations along the relevant equations along the way?
Yeah, I mean, I think I could probably put together a guide. Not that I know all the physics behind it, but making the radio was pretty hard. I was basing it off of a website called brimstar.org, and he has a bunch of projects. And I thought this would be something really cool. But actually putting everything together, being able to make something that you can tune, making these coils that you can tune, making these capacitors that you can tune, was really quite difficult. And it's really hard to troubleshoot. So me and my mentor were kind of trying to work through this. And it was a lot of understanding things called resonance frequencies, you know, how the length of the antenna would work. Would two antennas be better? And in the end, I was really happy. I was really surprised. And so are my parents. They didn't think I could do it. So
awesome. Great. And for the sake of time, if you have any other questions for Victor, feel free to put them in the chat and Victor can reply to the questions there. But for now, I'm going to pull up our next student presenter. Thanks so much, Victor.
Thank you for having me.
All right. Can you hear me?
Yep. All set.
Share my screen. Okay, so can you see my screen?
Yep.
All right. Well, hi, my name is Arul Shrivastava. I am a senior in Miami, Florida. When I'm not nerding out over the movie Interstellar or space in general, you'll see me playing the piano, guitar, or drums, or just making beats. I'm also a varsity soccer player, and I am a massive supporter of Liverpool FC, the best soccer team in the world. Today, I'll be presenting about how to measure star formation rates for a sample of local galaxies. So my aim for the research paper was essentially to use publicly available images and hopefully establish a correlation between star formation rates and celestial qualities like stellar mass, percentage abundance of gases, velocity, or average surface density. So for some background, our universe is kind of structured in a hierarchical manner. We start with superclusters, which are composed of about 5 to 10 clusters, which are further composed from anywhere from 2 to 50 galaxy groups. The image on the left depicts this structure, the magnitude of these structures. And for those of you who don't know, a light year is essentially the distance light travels in 1 year. As you can see here, our galaxy, the Milky Way, is part of the local group, which lies at the edge of the Virgo cluster, and all part of the Laniakea supercluster. Well, this research project is particularly concerned with the individual galaxy, which is composed of dust, dark matter, and finally, stars. Acting as fusion nuclear reactors by compressing their atoms of hydrogen and helium, stars formed in clouds of gas and dust known as nebulae. As stars constantly emerge, held together by their own gravitational force, an important characteristic can be measured: the rate of star formation. Simply put, star formation rates are the total mass of stars formed in a year measured in solar masses, and they are incredibly helpful in revealing details about a galaxy's morphology, evolution, and this is because star formation rates constantly change. One of its most popular applications, and I guess the world's favorite application, is in the Drake equation, which models the number of civilizations humans can communicate with, n, as a function of star formation rates, r asterisk. Well, so for the sake of regulation, there were a few parameters I had to work with when selecting galaxies, such as the mass had to be between 1 billion and 1 trillion solar masses. They must also be within a 15 megaparsec radius of the Milky Way, or in simpler terms, 50 million light years, and they must also be spiral galaxies. This last point is essential because, as aforementioned, stars form in clouds of dust and gas. In elliptical galaxies, however, there are negligible amounts of gas, and so there's little to no star formation rate in these galaxies. These first two pictures are natural and thermal images of spiral galaxies. These hot red regions are places with a lot of gas and hence a lot of star formation. An elliptical galaxy, however, has almost no gas, as you can see, and so there is no star formation in those galaxies. So stars are obviously the most luminous points in our sky. They're the main source of light in the universe. With this said, they emit a range of frequencies and wavelength outside and inside our visible spectrum. This happens because as electrons get excited, they move down energy levels, emitting photons with the equation E is equal to hf, f being a frequency and a specific wavelength. Now, for my research project, I focused on two of these wavelengths which are emitted, H alpha and far ultraviolet. H alpha is a wavelength coming in at about 656 nanometers in the deep red emission line, so it's in the visible range. Whereas far ultraviolet comes in at a wavelength of about between 100 to 300 nanometers, so we can't see it with the naked eye. I mentioned that H alpha images must be continuum subtracted, and you're probably wondering, I mean, what does this mean? Well, radiation encounters clouds of interstellar dust and gas as it travels to a detector, which means it gets absorbed or scattered. This means that if we were to use it, it would be a massive underestimate of the actual luminosity. And this is because of dust extinction. Dust extinction essentially works because the order of magnitude of the dust particles, when they're similar to the order of magnitude of the wavelength, they get blocked out and scattered. And so, seeing as how there are more tiny dust particles and larger ones, we use a larger wavelength to compare the H alpha image because larger wavelengths are not as impacted by dust extinction. On the left we have an R image. On the right we have an H alpha image. The R image is clearly more luminous, and hence we use this R image to compare the H alpha with. I then load both these images onto an astrophysics viewer, which is this called SAO Image DS9, and compare the flux for both the images. Flux will be very important in this project as it is defined as the amount of energy which is released by stars reaching a square centimeter of our detector. So once I find the flux of H alpha and R, I divide them to find a ratio between the two. Once I get this ratio, I essentially input the images into Python, converting the image into 2D arrays, 2D cutouts in an array. And I'm able to subtract the H alpha image using the continuum ratio of the R band image. So in this case, we would get 5884 divided by 570, which is approximately 10. Right. So on this slide, the left is a regular H alpha image, whereas this is a continuum subtracted image. You can see there's a massive difference in luminosity, which is why this process is so vital to my paper. I then load the images back into the viewer as the continuum subtracted version. And then I place an aperture, this green region is an aperture on a singular star with the specific radius and center. These are the center and radius for this galaxy, for example. And after this, I'm able to look at the flux on the image viewer. Now, FUV is easier to calculate because there's no continuum. The Galaxies telescope provides us with a unit of counts per second. And as you can see over here, FUV flux in ergs per second per centimeter squared per angstrom is equal to 1.4 times 10 to the power minus 15 counts per second. So we can then easily convert it to flux. Now that we have flux for both types of wavelengths, we use this very important equation where flux is equal to the luminosity divided by 4 pi distance squared. And hence luminosity is flux times 4 pi distance squared. Then we can convert luminosity to star formation rates because there is a list of constants available online, and we can then just simple multiplication convert from luminosity to star formation rates. Now, as scientific researchers, I think we can all agree that when we plot a graph of our results, there's nothing better than seeing a correlation coefficient of more than 0.9. When I plotted stellar mass against my calculated SFR, I saw a correlation coefficient of 0.9955, solidifying my hypothesis that there would be a relationship between stellar mass and star formation rate. The second best feeling as researchers is being able to justify outliers. When I zoomed into the first data points, I noticed that there was one outlier with a high star formation rate. As you can see over here, this star formation rate is 20, despite it being a relatively low mass. Well, this galaxy is known as M82, a starburst galaxy. These galaxies are known as starbursts because they have an exceptionally high star formation rate. And due to this current high star formation rate, we're able to deduce details about its evolution as a galaxy, such as the impact of its neighbor M81's gravitational pull. Hence, by calculating the star formation rates of galaxies and using it to deduce patterns, I was able to achieve my aim in this research paper. And hopefully there will be time for more research regarding active galactic nuclei, as well as velocity of galaxies, and just deducing more patterns related to star formation rates, because as aforementioned, it will be a very important aspect of astrophysics in the future. I want to thank my mentor, Mr. Hopefully Doctor soon, Mr. Imad. He was incredibly knowledgeable. He is incredibly knowledgeable, and he was so understanding. He's just been a very supportive person, and he's just a very knowledgeable person. I do hope his talk here works out. Thank you.
Really awesome. Thank you so much. And so we've got the Q&A open in the chat for anybody to ask any questions that they may have. I did see one person. Let me see if they want to share. Maybe not. Chandrakant, do you have a question? You're muted. If you can unmute, please.
I think you have to press the microphone button on the bottom to unmute.
If you can put it in the chat, if you could type it, then we can make sure we hear it.
Yeah, I think you're still muted.
Still on mute.
Mr. Patel.
We have another person coming in. Let's see. Hi, do you have a question for our presenter? Okay, let's make sure these questions get into the chat so that he can respond to them. Okay. I'd love just like a quick, this is outside of my field, but I'd love to hear, like, now I'm curious about this outlier a little bit more and what's going on there. If you can give me a little more background about.
Sure, yeah. Yeah, so, well, as mentioned, star formation rates, they constantly change, right, throughout their evolution. Now, this outlier, M82, was a starburst galaxy, which means that at this period in time, it has a very high star formation rate. And this tells us that something happened, right? Something happened to cause this. Well, after I found that this had such a high star formation rate, I kind of went backwards and looked at, you know, what happened to M82, right? So I realized that it kind of went very close to M81 in its recent history. And M81 is a very it's a massive universe, massive galaxy. And so the gravitational influence that it had on M82 was so significant, so immense that M82 started undergoing these massive changes, more interstellar dust, more gas, higher surface temperatures, which just all, I mean, it's a breeding ground for stars.
Awesome. That's really awesome that you were able to identify kind of the outlier and what was going on there in particular. Great job. And so keep an eye out in the chat in case those questions come through for you. So we have a question about, like, can you please suggest any references or books or papers in this topic inside the chat? So why don't you respond in there? But awesome. Great job.
All right.
I'm going to pull up Parth now to present. So Parth, get ready to be present here.
Hi, hello, can you hear me?
Hi, I can hear you and I see you.
Okay, let me share my screen. Can you guys see this?
Yep.
Okay. So my project is about predicting stock movements using machine learning. Before we start, a little bit about me. I'm on a robotics team with 5 friends. I run track at my school and I like playing basketball. I also like making beats and listening to music, and I do debate. So a quick intro about just what stocks are and the stock market is. Stocks are basically just equity in a corporation. Companies sell shares of their business to raise money so they can spend that money for new ventures. And these shares or stocks are traded on public exchanges. And the price of shares is determined by supply and demand. So if a lot of people want a stock and are buying a stock, the price will raise. So the reason I chose this project is I used to trade stocks myself, and I wanted to see if like an algorithm could trade better than I used to. Some other reasons are predicting stocks is very profitable. So if you can accurately predict where stock's going to go, you're going to make a lot of money. and they're also useful to predict where the economy might go. And I just thought that it was like a great application of machine learning, as we just have decades of of data that we can use to help traders. So the goal of this project is to create an algorithm that uses historical data to forecast whether Apple stock will rise or fall the next day. So I have like a very clear goal here. Some initial challenges, like just generally with the stock market, is that they're affected by countless factors. So every day prices are super volatile, and some of these factors I listed here were current events like company performance reports, and then just more general things like interest and inflation. So yeah, this data is very chaotic and it's constantly changing. And some research has even concluded that stock market data follows a random walk, which means that past prices can't be used to predict future prices. But a lot of other research has concluded the exact opposite. So I decided to give it a shot. So another thing I concluded after like reading about the stock market is that we need a non-linear model, and like something like linear regression won't work properly for this because the data is too random and volatile to be predicted linearly. So here, just a quick technical thing about regression versus classification. So in the context of this problem, regression basically refers to predicting the exact price of a stock, whereas classification is classifying whether the stock will go down or up. So just two groups. And I chose classification because it seems like I just chose classification because it seems more straightforward. And yeah. So the data set, we need a lots of data to teach our model because like I've been saying, the stock market is a pretty tricky thing to predict. Luckily, Yahoo Finance has all this like data easy to get, and it just like takes a couple lines of code to download like 20 years of past stock data for Apple. So the features, rather than just inputting raw prices to the model as the input, we can calculate technical indicators to give the model that information that can better capture patterns than just the raw prices. So these technical indicators are better at showing trends in the data. And another thing I did was convert the raw prices to day-to-day percent change of the stock. So as time goes on and for Apple and many stocks, they rise, there's no bias in the model there because all the data is just percent change, which doesn't change over time. And so to pick the features, I used a correlation table where I compared hundreds of indicators to the prediction value, which is whether the stock rose or fall. So I could see which indicators are most closely correlated with like the stock going up or down. And so these are two plots of two random indicators. You can see they're pretty like random and just like jumping around. Not really any patterns for us to see there. So let's see if the model can find anything. So pre-processing, we can't just input the data, or we can, but to make the model better, we want to input the data with some pre-processing. So first I smooth the data, and this basically eliminates any big outliers from the data set to make any patterns that are more noticeable for the model. And second, I scaled the data, and this normalizes it within a particular range, which I chose 0 and 1. And so it's a lot of the different inputs, the different indicators, range values. Like some go from anywhere from like 0 to 1,000, some are negative, but this will box all of them from 0 to 1 to make it more consistent for the model. So this is just like two graphs of the unsmoothed data versus the smooth data, and yeah, you can see like a little difference there. So now I'm going to talk about neural networks a little bit. This is like the model I've been referring to the whole time. Neural networks are made of many neurons, and how it works is data flows through your neural network it starts as an input and then ends as an output. For example, like a very common application is like maybe you input a image of like a dog, and then it'll pass through these layers here, and your output will be like the word dog. So these neurons are like biologically inspired, and they work similarly to the billions of neurons in our brains. which is they learn from examples and slowly become better at like any given task by trying different methods of like attacking the task and modifying its like parameters based on what happens when you try something. So now going like one level deeper into neural networks, this project is using recurrent neural networks. So basically this is a type of neural network, but that has an internal memory so they can remember important things about inputs they received. The neural network I described on the previous slide only considers the current input. And so it has like no context about where it is in time. Whereas with the recurrent neural network, we can look, it'll be thinking about the past when it's making a decision about what it's about to do right now. And yeah, so this is super important for stock market data where the data is in a sequence and it's like time series. And specifically inside recurrent neural networks, I'm using a long short-term memory network, which basically enables the RNN to remember inputs over a long period of time by extending the memory. So this is two graphs here. These are just a training and testing split. So all the blue lines of data is the data that will be used to train the model, and the green is what will be used to evaluate and test the model. So the model architecture, like I said, I'm going to be using LSTM layers. So you see there's the input layer, which has the second shape is 3, as we're inputting 3 days at a time to the model. And then there's 3 layers of the LSTM and then one final dense layer, which basically means a fully connected layer. And this final layer will have a binary output, like 1 for the stock is going to rise and 0 for the stock is going to fall. So more plots here. This is basically the process of the neural network training itself. And as you can see on the left plot, as time goes on, we see the accuracy rising especially for the training data, which is what the neural network is optimizing for, but also the testing data, which is what we want. And then that second plot there, loss, that basically means the error. So what we want is we want the error to go down. This is what the neural network is optimizing for. It's basically trying to make the loss as little as possible. And we can see that for the blue line, the loss does decrease, but for the orange line, it doesn't really decrease. And this basically just means that the neural network is optimizing for the trained data, but this isn't very perfectly transferring over to the testing data as, yeah, there's 2 different data sets there. And over here, we have a picture of like what's called a confusion matrix, which basically just shows what the model predicted for the test data. And so you can see that it has it has a tendency to predict up more than down. And yeah. So the model final results. The final model on the test data that was unseen to it earlier had a accuracy of 56%. And I think those are pretty good results, as technically that means your model will be profitable if you start trading with it. And some ideas I had for future work and like possible improvements to it where you can add a lot more data to the input. So some examples of this that people have done are what's called sentiment analysis, which basically means they like read article headlines or read articles and try to decide if this article is saying a positive thing about the stock or a negative thing about the stock. You can add fundamental data. Like right now, we're not using any of the, like maybe the income of the company, the revenue of the company. We're just using old prices of the company. And there's many other kinds of data used to predict stocks. And another thing is modifying the model architecture. So you can add different types of layers to further optimize it. And yeah, that is it.
Awesome. Thank you so much, Parth. We are a little over the time. And so if you have a question for Parth, please move that into the chat so that we can continue on with our student presenters. But great job. So Rithika, I'm going to pull you into present now. Thanks, Parth.
Is my audio on?
Yep, I can hear you and I see you.
How do I share my screen?
towards the bottom, there should be a little bar, and there's like a mic, a play button, and then like a monitor looking button.
Yeah. Oh, okay.
That's the one.
Can you see it?
Yep.
Okay, so hello, my name is Rithika. I am a junior from a small school in New Jersey. And so my research paper is about how SARS-CoV-2 is affecting the nervous system. So my goal for this paper was for people to truly understand what SARS is and how it affects the nervous system. Okay, so now, as much as everyone knows what COVID-19 is, no one really understands what the real meaning behind it is. Like, if I just ask a person, what is COVID-19? They'll just tell me it's a deadly virus that causes a deadly pandemic. So what SARS-CoV-2 is, it stands for a severe acute respiratory syndrome coronavirus 2. It is a virus that causes respiratory infections in humans. The most common side effects of SARS-CoV-2 are shortness of breath, cough, fever, change in menstrual cycles, and muscle pain. The most common post-COVID psychological side effects are headaches, dizziness, loss of smell or taste, mood disorders, anxiety, depression, and nerve damage. So even though like some people don't have SARS, it can, just by the pandemic, it can affect your nervous system. So after the global pandemic started, there was a more increase in anxiety and stress due to the reasons of indoor isolation, which led to negative impact on sleep, which is also known as coronasomnia, also known as insomnia, which has been really common during the pandemic. What's interesting is prior to the pandemic, about 24% of people suffered from sleep maintenance insomnia or difficulty staying asleep. But then after the pandemic started, that increased to 40%. So, so you may be wondering, why did they create a whole nother name, coronasomnia? So insomnia is caused by depression and anxiety. While coronasomnia can be caused by that, it is also caused by like the COVID-19 pandemic, and the symptoms are much more intense, such as lack of daily routine, distance from others, financial stress, emotional stress, and then unpredictability and professional concerns. And so solutions to this would be, I guess, improving your sleep hygiene, sticking to a daily routine every day, exercising daily, and not watching the news frequently, because that could build up anxiety. Okay, so what is the nervous system? The nervous system is a control system of the body. It controls your movements and sends messages to and from your body. Every voluntary movement human perform is under direct control by the nervous system. Our nervous system sends messages to control body's internal environment to maintain homeostasis. For example, if your body is heating up, our nervous system will send messages to start sweating, and so you can cool off. Our nervous system is really important because our nervous system is integral for our daily routine and function every day. So how is SARS connected to the nervous system when this is a respiratory disease? So while it is a respiratory disease, it can affect other organ systems, such as people infected with SARS have been complaining about headaches, fatigue, and brain fog. And brain fog refers to issues with memory, thinking, attention, and it can be difficult to explain for many patients. So, okay. So this is evidence of SARS neuroinvasion in a COVID-19 patient. So if you look at this image, right here, this is a brain autopsy of a SARS patient. And essentially, you obviously, when you're looking at this, you have no idea what I'm talking about. So this H&E stands for hematoxylin and eosin. And these are two dyes that are used to stain cells so we can identify parts of the cell. So these spike proteins that they're pointing at, they were actually clear white, but with this stain, they were able to identify the spike proteins in cells and in the brain. So obviously, you could see the viral spike proteins damaging the blood-brain barrier, because then how would they get into the brain if it didn't pass through the brain barrier? And essentially, the function of the blood-brain barrier is to shield the brain from toxic substances in the blood, and it will filter those toxic back to the bloodstream. Viral spike proteins allow viruses to enter host cells and cause infections. So essentially, this brain vasculature system is very complex, and even a tiny quantity of neuroinflammation can be highly harmful. If the blood-brain barrier is damaged or weakened in any way, this will allow immune cells to cross, and these then attack the myelin around the nerves, which leads to nerve damage. And if you don't know what myelin is this allows electrical impulses to transmit quickly and efficiently along with nerve cells. So now you may be wondering, like, how is spike proteins damaging the nervous system? So as soon as SARS is entered in your body, it binds with spike proteins and also the ACE2 receptor. And so the ACE2 receptor is a protein on the surface of many cells. It is an enzyme that generates small proteins that then go to regulating functions in the cell. ACE2 regulates blood pressure and maintains blood pressure in homeostasis. ACE2 binds with SARS spike proteins, and essentially, the way that spike proteins are break through the blood-brain barrier is by this specific linoleic acid, which is bonded with ACE2 receptors. And this linoleic acid can break down the blood-brain barrier. So as the ACE2 receptor is binded with the spike protein, essentially this could break down the blood-brain barrier, and it will allow the SARS spike proteins to pass through and damage neurons. And neurons are very fragile, and they can be damaged really quickly. And if they're damaged then this will cause muscles to stop working and a loss of feeling in the injured area. And nerve injuries can impact the brain, the spinal cord, and other nerves around the body. Thank you for listening.
Great, thank you so much. And so we have about a minute and a half for questions. If anybody has a question, feel free to put it in the chat or request to come on to ask directly face-to-face. Let me just double check. I can start us off with kind of a general question about the process of going through research. So I'm curious, as you were going through and learning all about this, what was most surprising to you from what you found?
So So when I was researching about like the nervous system and SARS, like at the beginning, my intention was not to figure out how is it affected. I was just researching about SARS. And as I was looking through papers, I just kept on clicking links on links on links. And then it took me to a paper about the nervous system and SARS. And the part that got me really surprised is that it's spike proteins that are damaging our nervous system, because our COVID vaccine essentially is spike proteins going into our body so it can protect us from COVID. So I thought that was pretty surprising that that could affect our nervous system as well, when it's supposed to protect us too.
Yeah, that's definitely an interesting complexity there.
Yeah.
Awesome. Thank you so much. And so if you have a few questions, if you want to hang around into the chat for a little bit longer, I do have to run to our next student session. But awesome job. And I want to thank everybody who attended and encourage you to continue to pop around to other sessions and panels throughout the day. I'm really impressed and proud of the work that all of you were able to do. Awesome job. And so I will see you around in other rooms. Thank you so much.